Construction of the hyperbolic filling itself is pretty straightforward. Our standing assumptions is that our metric space is bounded, which after a scaling by a finite number we can assume to have diameter strictly less than 1, and then we will fix two parameters, alpha bigger than 1 and tau bigger than 1. The ball centered at x0 of radius 1 is just all of our space. Let A1 be a collection of points in my space such that two conditions. First, for every pair of points in A1, we have that distance of x and y is more than or equal to alpha to negative 1, and A1 is maximal with this property. That is, you cannot add any one more point to A1 and still keep this property 1. This set exists by some argument. If in the finite case it's kind of obvious, but in infinite cases we have to apply something like Zorn's lemma. If you take union of the ball centered at points of A1, so x is in A1, you take the ball centered there with radius alpha to negative 1, should be all of x. Because if this union was not all of x, any point in the complement could be added to A1, violating its maximality. Now, we would like to think that A1 is kind of a net, a discrete net of points inside metric space X, but let me remind you that this doesn't have to be the case. For example, if your metric space consists of just 2 points with some reasonable distance between them, then A1 could be all of X. Another example could be you take any set with discrete metric, I think it's called, distance of any 2 points to meet that requirement, say 1 over 5. For certain alpha, I don't want to do this calculation, it's pointless. A1 will be just X. I'm going to set A0 to be just the singleton. A1 is some set that is alpha to -1 separated. So let's write this terminology then. So I is called alpha to the -1 separated. So when we say a set is some parameter separated, that means every pair of points are at least that distance apart. We find sequence of subsets of X such that, so this sequence A0 and A1 were chosen above, and then there will be A2 and so on for every natural number, such that each an is alpha to the -n separated. So they become finer and finer, and that usually means you need to add more points to your sets, but not always, as I will show in an example, and maximal with this property. It is not unique, these aeons, definitely, and so it's a maximal set with this property, with this separation property. Now the example that I just promised, take a finite metric space. There exists some n naught such that alpha to -n naught will be less than minimum of the distances of points in your metric space, and that would force this would force, because of maximality of an, they will have to be all of the space. So for every n bigger than or equal, even if you take all of your x, it is alpha to minus n separated, and no smaller set will do it because it's not maximal. So they will just become x forever. An example that we will keep visiting again and again is you take the interval. Let me put this 1/4 so that we're safe. Okay, so what happens is, initially, let's say you take some point. Let me also draw it a bit larger. So you have just x naught. We can take it in the center, why not? And soon you will see that actually I want to draw it somewhere different. So that will be x naught. And you see that radius of 1 covers everything. And then let's say alpha be something that forces us to add some new numbers. Alpha equal 9. Now for a1, first of all, you need to pick x naught. But if you take radius of 1/9, you go less than halfway to here on each side. So you need to add more points to cover things. Probably you need something here and something here. Maybe then you have x1 here and x2 here. And these 3 points hopefully are 1/9 separated, and the union of radius 1/9 of each together covered the whole space. And then when you go to next level, which is 9 to the power to 81, definitely you will need to add way many more points just to be separated and also maximal. Deeper geometric data, we need to record also overlaps of these balls centered at points in an. And when you are in an, you are at the scale of alpha to minus n for x in the collection an. And once we will do so in terms of a graph and edges in it. The hyperbolic graph. The hyperbolic graph G constructed with parameters alpha and tau. So let me put this parentheses because these were our standing assumptions, but I'm emphasizing that we have made some choices here. So I want to give you a graph, so I have to first tell you what the vertices are. So it has vertices union of an cross n, where n goes from 0 all the way to infinity. So this is our vertex set. So you had these choices of ans, but now you also remember at what level you picked those points, because without this n, these are just subsets of x. So if I gave you a point and said x actually is picked here, without knowing at what level you pick it, there's loss of information. So, and as my picture had hinted at, this original one, a0 has just one point in it, x0, 0. So this will be just a singleton at the very top. and this is very important vertex for us. We will denote it by W0, and it's the root. And then x0, remember, is also in the next one, so definitely x0 and 1 is there, plus possibly more vertices. And as we saw with this discrete metric, it could also be just infinite. It could already be all of x1. So there will be a bunch of x11s for x in A1. And next one will be previous points plus possibly new points, or also possibly no new points. So these will be all x2s for x in A2. In case later we need this notation, we can also set Vn to be vertices at level n, so just an cross n. So for edges, and I already am cheating a little bit and putting this metric space that I had originally down here. So the cheating part is that we will later see that this original space we have is boundary of this graph. So these edges will descend down to x, but that's far ahead of us, and we'll cross that bridge when we get there. But for convenience, I'm going to draw this here. What edges are inside my graph G? Okay, x at level n can be a neighbor and y and m only in two cases. A, n minus m is equal to 1. So they are different by one level. One of them is at level n and the other is at level n plus 1 or n minus 1. And okay, so let's say you are here. This is your x at level n, and then you are here at level n plus 1, which is m. And m is n plus 1. Okay, so the natural scale, the natural radius at level n is you have ball of radius alpha 2 minus n. And this is because x was in here, is in an. And then you have the ball at y of radius alpha 2 minus m. And you require that these have non-empty intersection. So if this happens, you declare these to be neighbors. Okay. The second case you have neighbors is when n is equal to m. You are on the same level, and here is where the role of the other parameter tau will come in. You similarly want these balls to intersect, and they are both at the n level. But this time, very importantly, you have to help these balls by multiplying into tau, which was bigger than 1. So you're being a bit more generous. More vertices are likely to be neighbors because you enlarge the balls. X and y here. So in the metric space down here, remember y and x are points, so x, n, y, n. So these are after all points in metric space x and y. So you take these, let me maybe use this, you take these neighborhoods, and then if they intersect, then you draw an edge between them. So then this becomes an edge between them. And then you do this for all of the graph. X0 will be connected actually to everything, because the ball of radius alpha to 0, which is 1, is all of your space, so everything definitely intersects that. And that's important because ultimately we will need our graph to be connected, and if everything is connected to the root, we know that there's at least one path between any 2 points. So you do this and you just keep going down. Also, you can see that all the vertical edges will be there. There will be of course possibility of having multiple points mapping or being connected to one down here, or one point coming down from a few of them. One thing that is provable is that every point will definitely be connected to something from previous generation. So nothing will be left alone isolated like this. So we make G a metric graph. We turn it into a metric space by gluing a copy, an isometric copy of 0, 1 segment to each edge. So we view each edge as being an actual edge, a line segment existing between the two vertices, which is isometric copy of 0, 1. So my pictures are not necessarily embedded in R2 because these lines may have to cross each other, apparently cross each other, but every 2 of them will be really a different line segment. So other than at the vertices, they will never intersect. And also in my picture, because I am drawing in R2 basically, I'm forcing it to be embedded, some edges look longer than the others, but all of them are just copies of 0, 1, so they are all same length. And also remember, I have to repeat this for infinity. My pictures will always necessarily have to get shorter and shorter, but keep in mind that even when I draw it this long, it's just a copy of 0, 1. Later again, we will indeed play with these distances and kind of make them actually shorter, but we are not there yet. We define a distance of points in this graph, which now also could include points in between the vertices, like on an edge. So we want it to be infimum of length of gamma, where gamma joins x to y. So this length is well defined because each edge is copy of 0, 1. So if I go back to my picture, if I am here, okay, and I want to compare the distance to here, one possibility is to move along this edge. That is 1 length plus 2 plus here 3. So the distance is about 3. Maybe there will be a shorter path. Maybe actually this and that have a horizontal edge between them. Then that would make it 1. But at least there is one path. And remember the 2 facts that I said. Okay, let's write this down. Facts. Each vertex, say x at n plus 1, is connected to some vertex from previous generation, some y n, and this implies that G is a connected graph. Therefore, this distance is well defined. It's not infinity. There's at least one path between any 2 points. You can go all the way upward to reach, so you can repeat this to go z n minus 1 and so on. You can repeat this and go all the way to the root, and then do the same with the other point. in finite time, which is at most this much, you reach the root, and then you can connect the two, so the distance will be at most the sum of their integer parts, their levels. Okay, in fact, you can actually prove that if v is x and n, that is, it is in level n, then first of all, there is this, again, vertical upward path to the root. So distance of v to the root, which we denoted w0, is at most n, because there is a path of length n, but also you cannot do any better, and easy to show, so that's n. So far we have built this infinite graph. It will always be an infinite graph, remember, because the levels keep going up even if ends become constant, like in our finite case. I'm going to do the example in a second. And we have assigned a metric to it.